kind of show you some things. I just hit record and let me get the chat open and then share my screen. And I hope you guys are all doing super great. I've had a few little crashes and things here and there. So let me know if things aren't showing up super great on the computer screen, like the Zoom starts putzing out or something like that. Just let me know, because it's been a little bit of an issue the last 2 days or so, starting last week on a couple of different classes. But I think we'll be okay here with all the Stan State ones. It seems to be more stable at Stan than MJC. So here's what we're going to be looking at today. We are going to be talking about earthquakes. Looking at earthquakes is kind of like part one. And what we're going to be talking about here today is trying to identify some of these different faults, trying to figure out how they're made and how we can kind of triangulate where we can find their position in the world, finding their epicenter basically. And then we're going to kind of end tonight learning about the earthquake early warning system. There's an app that you should totally download to your phone that will give you warning when an earthquake has happened and how much time you have before the earthquake hits you, so you can drop cover and hold on and stay safe. So that's kind of where we're headed tonight. And then next week we'll be looking at the differences between earthquake magnitudes, earthquake intensities, and trying to figure out basically, why can some big earthquakes not cause much damage, and why can some small earthquakes cause devastating damage? And we're going to see some of the hazards and some of all that other stuff that goes along with that. So like I said, let me get my pointer thingy here. We have we're going to talk about faults, figure out how those are, how to determine them, kind of figure out what stresses are being applied there. Earthquakes 101, then we'll do earthquake location activity. Maybe just very briefly, I think we'll skip this one just because there's a little bit better stuff to spend our time in. But we will be taking a look at how earthquake waves move through the earth. And then next week, like I said, we'll be applying all this knowledge to hazards and things like that. So a couple of things, the Geo News you need to Geo knows. That was Yosemite this morning at about 9:45 from Sentinel Dome. You can see some little funny white stuff right there. And that by this afternoon, as of about 4:05 from the webcam that's up there. So this is the same view here. Just you can see not much snow is left. So they got a little dusting of snow above 10,000 feet, somewhere in that neighborhood. And depending on where you live, we all woke up with a few different traces of rain. In Turlock, where I live down here, I had a wet sidewalk, sort of, but nothing registered on my rain gauges, so it officially goes down as a trace. But there is a weather link here if you're ever interested to figure out like the official weather totals. Oops, gosh darn it. If you're ever interested to figure out the official weather totals, that link will take you to this interactive map, and you can see how much rain different stations got in different places. And remember, in Turlock, our average for the whole entire year from October 1st to like September 30th is about 12.8 inches in Turlock, somewhere in that, or 12.78, something like that, right around there, give or take a few hundredths. So this is just a little a spit in the wind, I guess, but it's better than nothing for a lot of folks, and ended the 209-day drought or 204-day drought since there's been rain for a lot of folks. So they can do rain on this map. You can also do wind gusts, and you can see how strong the strongest winds have been at any given point at different stations throughout the day. So I haven't really been outside much today because I've been teaching all day, but apparently there's been a gust of like 10 miles an hour in a few different places. So this is kind of a handy dandy little map from the National Weather Service if you get a chance to take a look at it someday, if you need to, like if you're trying to plan vacation type things. And I was going to see if I could find a little update on the weather forecast for like even further into next week, but couldn't find anything relevant. But here's what is relevant, since I won't see you again until next Friday or so. This Monday morning, or this coming up Monday through Tuesday, we are going to have very strong wind event for the Central Valley here. So we could see wind gusts, so sustained winds of about 20-25 miles an hour in Turlock, with sustained, or that's sustained winds, like constant 20-25, and wind gusts up to about 40-45 miles an hour, maybe even a little bit higher. It just kind of depends. So if you have any busted up fences or anything that could blow over, or if you have what do you call it, like those sunshade umbrellas or things like that, you might want to bring anything that can blow away inside on Sunday night, because Monday, Tuesday, it's going to be really, really strong. And there could be some really strong winds also in the Sierra Nevadas. No wind, I mean, no rain or no snow or anything is associated with this, but super windy, could snap trees off, branches go down, things like that. And what's really bad is, if you notice, all of our leaves are still on our trees outside. So that adds extra friction and force when wind blows through. So there's a higher likelihood of these wind events early in the season, causing tree branches and stuff to break down. So just be aware of that. And it's also going to be super dry, which means dry, high winds, super fire danger, right? So if anything catches in the foothills on either side of us, or even in the valley, it could be not so great. So I would suggest Monday and Tuesday, not a good day for barbecuing. All right. And if this is kind of what it looks like up from, if you're looking at the wind from about 15,000 to 16,000 feet up in the atmosphere on Monday, this is what it's going to look like. And you can see down here on the bottom, it's like 116 mile an hour winds up high. And these jet stream winds, they're called, really influence the winds down at the surface. So if I click on the surface, you can see kind of these sustained winds of about 21 miles an hour are forecast with the big strong models that we have here. So we're going to see in a few weeks, you guys are going to be pros at predicting where wind is and how we know where wind is and why it spins and goes the way it goes. But first we got to get through the solid earth, and we'll get to the other stuff a little bit later on. But I should also mention, you notice that this wind is kind of coming straight down kind of the coastal parts and in from Canada. So it hasn't had much time to go over the ocean to gather a lot of moisture. That way it's going to be kind of dry and just not super wet and produce any rain for the next couple of days. There's hints at something maybe Friday, Saturday next week, but I haven't seen the latest models, and that's what I'll just leave it at that for right now. So that's kind of the geo news you need to geo knows, and I hope y'all take it to heart and bring in your stuff that blows away. So the other thing here is then what are we looking at here today? Well, we're going to be talking about what is an earthquake. We're going to be looking at a few notable historic earthquakes in California. And today there is one in 1867 on this date, October 8th, 1867, that was the first San Francisco earthquake. Mark Twain wrote about it, and a few other folks. So it wasn't the big 1906 one, but it was a really big 1860, what did I say, 1867? Yeah, 1867 is when that one was. So we're going to look at some historical ones. We're going to have to figure out what the difference between an epicenter and a focus is. We're going to look at our 3 different types of faults, and I'll take some time to sketch these out with you so that you guys can kind of see how I draw them and come up with a few different California examples of where we can find these. Then we're going to take a look at seismic waves and the types of seismic waves there are. We're going to sketch some of these interesting tidbits about the S waves and the P waves, which move through the body of the earth, and a couple of different waves called Love and Raleigh waves, which move through the surface of the earth, or roll along the surface of the earth. You're going to just kind of sketch a simple little seismogram, which is the squiggly lines that you see in all the movies with when earthquakes happen. We'll figure out how to find the epicenter of an earthquake. And then the last bit here is you're going to make a quick little infographic that explains how the California earthquake early warning system works. So if you had to tell it to a 6th grader, how does this system work? Here's how you would do it. But you should include things like, hey, like a fault or an S wave, P wave, seismic stations, ground shaking, cell phones, drop cover, hold on. These things should be included in there, and it'll make total sense. It's pretty easy to see what happens after you see the little video clip. And it'll be nice because this will likely save some lives someday, and maybe it could be yours, which is kind of cool to think about. Oh, let me, come on, computer, escape. What the heck? There we go. There we go. All right, so perhaps you recall back in like the 4th of July in 2019, 2 years ago, if you were in Southern California, or you knew anybody in Southern California, uh, there was a pretty big little series of earthquakes happening out over by the town of Ridgecrest. And there was a magnitude 6.4, which led to a whole bunch of little aftershocks. And then boom, a larger magnitude 6 or 7.1 hit just a few days later. And what's kind of cool is, sorry, my kid was yelling. So what was kind of cool about this is normally when you have a 6.7, there's only a 3 or 4 or 5% chance of having an even larger earthquake after it happens. And so this one, though, that 6.4, it had all of those little guys shaking around like this. And so we end up calling those foreshocks because after all these earthquakes went, we had a magnitude 7.1. So anything that came before that big 7.1 is what we call a foreshock, small earthquakes or earthquakes smaller than quote unquote the main event. And then anything that happens after the main event, we call it aftershocks. Now, the thing that kind of stinks is you can't really always know if it's going to be an aftershock or if it's going to be a foreshock until the main event has happened. So sometimes the smaller events go and nothing bigger happens. And then that's just what it is. So we're going to learn, there's some statistical probabilities later on that keep us safe, that help us understand, what is the likelihood of a bigger earthquake happening after a smaller earthquake. So there's a bunch of those things that we'll start looking at a little bit next week. But for the most part, this is probably the most recent example of strong shaking that most folks in California have a remembrance of feeling. So this one, I know it like shook swimming pools even in Northern California slightly. And so some people felt that. So perhaps you felt that. And I just have a quick question. How many of you can just chat or whatever, or emoji or whatever. How many of y'all have felt an earthquake before? Have you guys felt any strong earthquakes? Have any memories of an earthquake? Oh yeah, Sarah, yeah, all right, yeah. Couple folks, nice. Oh, Sarah, were you raising your hand just to say yes, or did you want to say something?
I was saying yes.
Oh, okay, awesome. So sometimes people raise their hand and they actually want to talk to you. So yeah, and this is great. So a lot of folks have probably felt them, but they've kind of probably, unless you're, 35 or 40, probably, not the most large ones, unless you're down in Ridgecrest or something like that too. But the reason we need to learn about this is because in our lifetime, I can almost guarantee that sometime within our lifetime, next 30, 40 years, 50 years, somewhere in that neighborhood, there's going to be a rather large earthquake somewhere in California. So we have to be ready and prepared for it and, hopefully stay safe. So California, right, we have our faults. This is from the 1989 Loma Prieta earthquake right in there. That caused a lot of damage down in the Marina district. And that was 1989. So what does that make that? How many years is 89? 31 years ago?
32.
32, yeah. Okay, I'm doing my math. Yeah, thank you. 30, I have brain fog still. But yeah, 32 years ago, this is that earthquake happened next week, 32 years ago, when the Giants and the A's were playing in the World Series. And that had some big kind of repercussions here in the Central Valley and also in the Bay Area about how big that was. So here's the first thing I want to ask you. This is kind of the hazard map of the United States in terms of, if you read the bottom here, it says 2% probability of exceedance in 50 years, in 50 years map of peak ground acceleration. So what this is showing is reds are areas where the ground would accelerate very quickly during an earthquake, which means there's going to be a big like there's possibility for big, fast, sudden movement in those areas from an earthquake. All right. And this is the chance that it could happen, like the 2% chance within 50 years, somewhere along these lines. So basically what this means is where the colors are redder, much higher chance of having an earthquake somewhere along that area. All right. Where it's whiter and grayer, less likely, probability of having an earthquake. So what are some things you notice about this map here? If you know, the red areas are kind of like areas where it could be strong earthquakes or strongly felt earthquakes and shaking around there. What do you notice about different areas on here that stand out to you? And you can just chat it, you can say it out loud. Like if you're comparing one place to another, like what are some things you notice about this area? Or earthquakes in general here in the United States?
Would it be that California is super red around there?
Yeah, California has a lot of red, right? And if you remember from our plate tectonics stuff that we talked about, what fault boundary is this? What name have we given this fault boundary? Like, and there's movies with the rock in it. Yeah, the San Andreas. So this is the San Andreas Fault. Yeah, so anywhere around there, that's our San Andreas Fault, and it kind of moves up into the Pacific Northwest. So definitely the strongest shaking there, for sure. What else do you notice about this map? Is California the only place, or like anything stand out to you that's kind of weird or it's unusual or something you wouldn't expect?
Towards the top, like in the middle, there's nothing.
Ah,
Like no
yeah.
color.
Yeah, not much color at all up there, right? So if you're looking, and these are what Dakotas, right? South Dakota, North Dakota, Minnesota, Wisconsin. Yeah, there's not much happening up there. And that's some of the oldest rocks on our continent. You know, those are the billions and billions, couple billion-year-old granitic rocks up there that are super cold, don't have much pressure on them. They're away from the fault boundary. So yeah, they don't have many chances for earthquakes up there. But
Is it also a different plate, Professor?
oh, that's a great question. So no, these are all, so this is all on the North American plate. Well, at least I should say everything on the east side of the red San Andreas, that's all the North American plate. And then the Pacific plate would be over on the west side of the San Andreas over there. But that's a great question. But yeah, these are all, so technically this is all one big plate unit, part of the North American plate. Would go up into Canada and stuff like that too. How about this? And if you guys know your geography here, here's Missouri and Illinois, right? And then like Indiana and oh man, Tennessee and Kentucky and all these places. Does it seem weird that there's a really high risk of earthquakes out there to you? Or South Carolina, or you know, Eastern Tennessee? Like most people don't think of that as earthquake country. And even people that live there don't know it's really earthquake country. But the old Appalachian Mountains that are here, they used to be, remember they formed from plates colliding together to make Pangaea before Pangaea then broke up. But you know, 400 or 500 million years ago, these were huge mountains being smushed like the Himalayas. And there's old kind of faults left over from those mountain building experiences, and every once in a while they let loose. And I believe it or not, it's hard to imagine for most folks, but the largest earthquake in the lower 48 United States, so outside of Alaska, was right here along what we call the New Madrid Fault back in the early 1810, 1811, or somewhere in that neighborhood. Magnitude 8, probably 8.1, 8.2 earthquake, somewhere in that neighborhood, that caused the whole entire Mississippi River to flow backwards. So it's huge. And it was just one of these old faults that kind of got activated again. They're not frequent, but they have lots of stress on there, and it does happen. And the same thing over in South Carolina, like over by, yeah, I think it was like Charlottesville, South Carolina, right? There was a big earthquake there right after the end of the Civil War that kind of destroyed things. So that's kind of some interesting things. And notice also in California here, though, the Central Valley, kind of where we live, we're in this kind of yellow to greenish area, mostly yellow and darker yellow where we live. So in terms of where shaking could happen, we will probably feel some stuff, but it's not going to be as bad as some of the other areas, right? So that's kind of the good thing about Turlock is, yeah, we got a little bit of shaking to deal with, but it's not freezing cold. There's no hurricanes, there's no tornadoes, right? There's none of that. So I like Turlock. It can be, you know, boring and crazy when you're young, but in the end, it's probably one of the safest places, geologically speaking, to be. It's just Now we got to worry about water. And here's another way of looking at that map as well. The hazard map just kind of zoomed into California. And you can see Turlock's like right here. So we're kind of in that lower risk area compared to everything else. Doesn't mean we won't feel shaking. We definitely will feel shaking in the '89 earthquake, the Loma Prieta earthquake in San Francisco, or happened in Santa Cruz. But I mean, the ground shook here for 25 seconds, and like the street was rolling, and it was still one of the craziest experiences of my life. And you know, we will all feel that too, eventually again, very soon. And so if you're unsure, you know, will we see that again? Well, check this out. This is all of the historic earthquakes here of magnitude 5 or greater since we basically have been able to start keeping records and trying to determine how big these different earthquakes are. And you'll notice a lot of them, most of those big earthquakes are right along the San Andreas Fault or near the San Andreas Fault. But we also have some out where the faults are extending, where parts of the continent are trying to stretch apart. And so we can actually get some fairly large magnitude 7 earthquakes out here as well, which is, we'll see why that's important moving on here. So California, we have lots of earthquakes. We have tons of earthquakes every day. We have, well, probably somewhere in the neighborhood of, you know, 400 or 500 earthquakes each day in California that are pretty small. And if you were to open, if you were to open that interactive map that I was going to show you here, maybe, there we go. Maybe, okay. You can see there's all sorts of them here. And so this one is just kind of, this was like all the largest earthquakes that we've had. But if I go over here and reset this to make it last 7 days, all magnitudes in the US, and have it show everything on this map. If that's 1 day, I want 7 days. There we go. You can see what are all these different earthquakes right here. So on this map alone, there's 2,300 different earthquakes. And most of them, as you can see, are in California here. So 2,300 different earthquakes just in the last 7 days. So we've got to live with them. Mostly they're small and the ground is shifting and moving around. And we're still, look, here's that ridge crest like I was showing you at the beginning of class. We're still having all these earthquakes aligned on those faults. These are still all aftershocks, old aftershocks from that ridge crest quake. Oh, question, but Valeria.
So you mentioned how there's like mini earthquakes because the floor is moving. Does the floor move regardless if there's movement? Like if humans were to vanish and animals and nothing would move the floor like cars, would the floor still move, or is it just?
So are you talking like the crust of the earth here, or?
I'm assuming, yeah, I guess.
All right, so so I said like the floor was moving.
You mentioned, well, you said how there was mini or small earthquakes because the ground is shifting.
Oh, okay, yeah.
And so I'm wondering if there was to be no humans, no movement at all, will it still shift?
Oh, okay, that's a great question. So if nobody was here to feel it, would it still shake? And the answer is yes. And so, yeah, that's a good question. And so what's happening here, these earthquakes are just kind of the expression of the plates moving past each other and smashing past each other. So we looked at volcanoes, but before we did volcanoes, we looked at how we had the convergent boundaries and the transform boundaries and the divergent boundaries. Basically, what earthquakes are measuring are just rocks breaking. And as they break, they're going to release energy waves because there's some stress that was built up in them. And when they release those energy waves, that's what goes out and that's what we end up feeling. But if there was nobody here to feel it, it wouldn't be recorded anywhere except in the rocks. But definitely the shaking and stuff would still happen and be there. And kind of a really cool example of that is on Mars. We just, so we have a couple of rovers, but 3 years ago, we landed a probe that went onto Mars and drilled in a seismometer, which is basically something that measures the earthquake waves. And they drilled it into the ground, not knowing what to expect. And sure enough, we have Mars quakes. We've measured Mars quakes, and they measured like a magnitude 4.5 on Mars just a few months ago. And so nobody's been there for, ever for 4.5 billion years. Well, maybe, we don't know. Maybe there was life before. We're trying to figure that out. But yeah, even though nothing was there, earthquakes have been ongoing, and we can see that from the resulting breaks in the faults and the rocks. So yeah, these are good questions. And no matter if people are here or not, they're going to keep happening until the Earth's interior basically stops having heat. And once the Earth's interior stops having heat, which we think will probably run out in 5 billion years, it won't matter because the sun is not going to be around in 4.5 or 5 billion years. So the solar system won't exist. And you know, but that's basically so far in the future, it's like never going to happen. So hypotheticals, but yes, the earthquakes will continue going as long as there's plate tectonics. And things will feel it. People will. Rocks, I mean, I don't know, they have feelings, but they'll record the earthquakes for sure. So that was a good question, thank you. So some of the California historical large earthquakes that have happened, we have the San Francisco earthquake back in 1906. It's probably about it was a magnitude 7.7 on today's scale. And we're going to see next week that when we go from like a magnitude 6 to a magnitude 7, that means the amount of shaking increases about 10 times. All right. If we go from a 6 to a 7, the amount of energy release, though, is 32 times greater. So basically, when I show you this one and then I show you the next earthquake, which is like a magnitude 6.7, this earthquake was like 32 of the other ones happening at the same time. So take a look when I show you these pictures too of collapsed buildings and things. Let's see what all these buildings have in common. All right, so that was City Hall in San Francisco. This was at Stanford University. One of their statues plummeted and hit the ground. It's kind of one of the funny pictures that everybody still shows from this one. But you know, you don't want to be outside when that was happening. And then we had in Long Beach in 1933, there was a magnitude 6.4. And the reason this one was, well, so I should say, this one was really big for California because it almost destroyed San Francisco. 2/3 of the city burned to the ground after this earthquake because water lines were cut off and things like that. So that had a big effect on how water operated in California. Then we had the Long Beach 1933 quake. And this one down by like Long Beach Poly High School and Compton Unified and places like that. What was so interesting and so unique about this one is it hit a lot of schools and did a lot of damage to different schools. And so you can see that, oops, where to go? Here's Long Beach or Compton Junior High, another one. This earthquake, even though it wasn't like super huge, is magnitude 6.4, it did so much damage to schools. It did a lot of injuries to people. And this is one of the reasons why we don't have or didn't have 2-story schools in California for a very long time after, is because it was a lot of these 2-story schools built out of what? Do you guys see what's kind of the common thread of all these buildings that have collapsed here? What are they built out of?
Is it brick?
Yeah, they're all brick. And it turns out that a brick house may be mighty, but it sure can come tumbling down when it's not appropriately engineered. All right. So bricks, they stack up nicely, but if you start introducing a side-by-side motion or a motion that kind of goes like this, it's like kicks out the legs from underneath them and can cause things to collapse. So this is why we also don't have old brick building schools in California very much anymore, unless you went to like Turlock High. The old Performing Arts Center at Turlock High is old and brick, and they've done their best to retrofit it as much as possible. But should there be a really big earthquake in California nearby, that is not the building I would want to be in if there was a large earthquake. And I think like for the folks that were getting kicked out, she apologized, and then oh no, your guys' videos are freezing. That stinks. All right, so let me see here. If that's fine. If you guys have to get bumped out and rejoin, that's okay. Like no stress on my part. So yeah, I'm just getting little direct messages here. So well, other people are getting kicked out. Interesting. Well, if you're here, that's good. I don't know why it's kicking people out. but don't stress too much, right? It's being recorded if you miss a piece here or there, and I promise we'll put it up. Yeah, don't stress, don't feel bad. I don't know how to stop things from getting kicked out. So it's not me doing it. That's what I should say. All right. So that was the brick buildings in Compton. And then kind of the other one that started changing us was the Loma Prieta in 1989. This is the one that I felt. I was in 6th grade back then in Turlock, but you can kind of see how this energy just starts unzipping, and the intense shaking kind of spreads out along the San Andreas Fault here as it starts busting along. And sending out those waves. So you can see kind of light shaking waves going out first, and then the intensity of the shaking picks up as time goes on, and we'll figure out why that is in just a little bbit. But you can see right here, pretty intense shaking in that area, but there wasn't a lot of folks to be there and feel it, so that was okay. But you also notice there was also some like a little bit of red here and a little bit of red up there, far away from the seismic waves. But it turns out that the types of stuff that buildings were built on over here shook more because it was built on mud and other junky material that helped cause some collapses. So that Loma Prieta earthquake, while that was notable, the reason that was notable is it caused a lot of a couple pieces of highway to collapse. The Nimitz Freeway. This is where most of the deaths occurred in this instance. The concrete pillars just collapsed on top of one another. We'll figure out why that happened next week. The Bay Bridge, the old Bay Bridge, collapsed and people couldn't get across there. Remember, this happened the day of the World Series at Candlestick Park in San Francisco between the A's and the Giants, and the whole Bay Bridge. It's called the Bay Bridge Series, and the Bay Bridge collapses in a big earthquake. So the reason that was such a big deal is because that earthquake has now spurred almost $80 billion, at least $80 billion of investment by these different counties in the Bay Area to retrofit and upgrade. That's what I'm trying to say, retrofit and upgrade all of the buildings in those different counties so that they won't collapse, and have bridges. This is what they spend the money on, basically, so bridges don't fall down, so that train tracks and subways and BART doesn't stop working or doesn't like smash together or things like that, to keep hospitals up and running. Because you're going to have probably lots of injured people during a big earthquake. So if we can keep the hospitals from falling down and we can keep them operational, that's going to be a big, huge part of making sure the communities can come back pretty strong, making sure our water supplies are safe and our school facilities are safe. So that earthquake alone spurred huge spending, even throughout the state. We started retrofitting and wrapping highway overpasses with like carbon fiber wraps so that they wouldn't shear off or get broken during a big earthquake. And if you've been to San Francisco recently, since 2013, this is the new Bay Bridge that you have to cross there. It replaces the old one that collapsed. They did a fixed job on it, and then took another 20 some years before this one was built. And this one is supposed to be able to withstand like a magnitude 8.4 or something like that, 8.5. So we'll see. It's a good design. There are some weak steel parts in it that they're trying to fix. It's already starting to corrode. So, it is what it is. And then the other big one was Northridge in 1994, down in Southern California, way down here. And this happened on what we call a reverse fault. So this earthquake happened in a really compressive environment, and it all just kind of jumped. And what separated this one from like this Loma Prieta, they're about the same size, but this one released the same amount of energy, but in about half the time. So it was way more jolty, and it really caused structures to just get collapse and bent over. And this was at Cal State Northridge. They built a brand new parking lot, and before the parking lot was about to open, the earthquake hit and the whole thing just crumbled. And so we'll figure out why that was later on. So that one ended up making California invest a lot more in houses and other structural upgrades, especially in Southern California. We learned that there were a couple of different types of faults that we weren't really aware of down there. And then they started building back better, I guess is the way to put it. Then I don't know if you guys remember this, 2014, I can't believe that was like 7 years ago already, but there are some strong shaking, and now we start getting into the era of people having like security cameras recording stuff all the time, rings and nests. Like now it's commonplace, but before 2010 even, we just didn't have very much going on here. So that strong shaking ended with a few little brick buildings again collapsing, historic stuff. Wouldn't want to be standing underneath here. That's why you don't go running outside in an earthquake. You drop, cover, and hold on underneath a desk or a chair. All right. And like the thing that I remember a lot is this picture of the earthquake caused some of the street to buckle, and then the Napa kids all went out and they started skateboarding using the earthquake buckles as ramps to skateboard, which I thought was pretty hilarious. And then of course all the wineries in Napa, just multi millions of dollars in losses of broken wine barrels and things like that. So people really crying over spilled wine. And now guess what? When they built back, they've now built all these different things so they can't fall over during an earthquake. They're engineered so that they don't tumble and they don't break. They have little straps around them. And that little bit of engineering is going to save them millions and millions of dollars if another earthquake hits, right? So here's what we're just going to introduce a couple more things here. Then we're going to take a quick little break. Then we'll get into some group work finally. And it's kind of fun. I think you guys will enjoy it. And then we'll go from there. So what is an earthquake then? So we've been talking about it. Well, here's kind of the actual definition. It's basically just the movement and the shaking of the ground due to rocks breaking or somewhere in the crust breaking and moving suddenly in the Earth's crust, and sometimes in the upper mantle, right? That lithosphere where it's nice and cold and brittle. And that movement releases waves of energy. It's kind of like throwing a rock into a pond and you see the waves ripple out. Well, energy is stored in rocks too. Kind of like if I were, oops, I know you can't really see it very much, but I have a ruler in my hand. If I were to take and bend this ruler, there's stored energy in there. If I let go, you could like, oops, I know you can't really see that, but you could, I don't know, like this. You could use that stored energy to like fling a piece of paper or something like that at somebody. Or if I held it with both hands and kept bending it, it would finally snap and break in the middle. And then you would hear the loud sound of the snap, which is one form of energy release. And then in my hands, I definitely would feel the vibrations of that breaking happening. So think of the rocks as kind of like springs. They're getting loaded with that energy until they can't hold it anymore, and then they snap and then they go. And so this is one of also my favorites. This is from 2010 in Eureka, Northern California, Humboldt County. And they had an offshore earthquake right up over here. And you'll see the dog is kind of like da 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 da. Kind of looks down and is looking around. And this dog, what happened here is he started hearing the first of the earthquake waves that was traveling towards them. So the earthquake had already happened out in the ocean, and then it heard the waves, and watch how it reacts. Ooh, it's out of there. And then the waves hit the chair, and the person who was sitting in the chair is like, what the heck was that? Oh, earthquake, boom. And then here come the big surface waves. So all these people, this is kind of before Drop, Cover, and Hold On was a big community kind of advocacy program. And so everybody was running out the doors. This is not what you want to do during an earthquake. You want to drop, cover, and hold on, because things can fall off and hit you in the head. And most of our buildings in the United States are designed to not fall down during an earthquake. So you're safe in the building, but you're not safe when you have stuff flinging around like this and could fall on top of you and just dome you and not be good. All right. So here's kind of a representation of what that looks like. These, what we call these planar surfaces. So imagine this is a piece of rock, kind of like if you're looking down in an airplane, like just a satellite view. And let's say it's the San Andreas Fault even. So the San Andreas Fault would kind of be in the middle of this rock. If there was no stress applied, it would just be rock. But if you start applying stress to either side of it, that rock starts bending, or the scientific word for that is deforming, right? It starts deforming underneath all this stress. And eventually those minerals can't hold that stress anymore and they break. And when they break or rupture, that releases that energy and allows the rocks to slide past one another. So it's kind of like if you put your hands together and you were trying to slide your hands together, but pushing down at the same time really hard until poof, it slips apart. Same thing happens with the earthquakes here. All right. The more friction there is, the harder it is to move, the more stress you need to apply. And if in the real world, if faults were perfectly flat like this, it would be easy to predict them. We could tell exactly when they were going to break. But because faults are made of rocks and minerals, and the rocks are not all the same throughout the whole entire world, and they differ at different depths, and because some of them are more jagged than others at the microscopic level, the amount of friction is too hard to measure, right, on a specific thing. So what's kind of interesting and weird about faults is we can measure how much stress is on those rocks. We can measure that with strainometers, they're called. They measure the strain and the stress on the rocks. We know in labs how much stress and how much strain it takes to break a solid chunk of different types of rock. So as scientists, we can say, wow, these rocks are super stressed out. They're going to break sometime. And based on the amount of stress there is, we think that this stress is going to probably cause these rocks to break much sooner than later. That's about as far as we can go with earthquakes. We can give probabilities of how likely a certain section of a fault is to rupture. We cannot, and I just want to say this now, we cannot predict earthquakes. All right. We can't say like on June 5th, we can't say June 5th, 2025 at 3 a.m. there's going to be an earthquake. All right. We cannot make predictions like that. But what we can say is, the northern part of the San Andreas Fault is probably not going to have a big earthquake on it before the southern part of the San Andreas Fault, because the southern San Andreas has a lot more stress built up on it. So we would expect down in LA, odds wise, LA would probably have a bigger earthquake before Northern California has another bigger earthquake. Doesn't always happen. Odds always don't, play out right. But mathematically speaking, that's what we're talking about here. All right. And that's because the rocks are all messed up, and it's really hard to predict that way. So a couple of things. So when we were looking at those earthquakes at the very beginning of class here, I said that those faults occur where stresses eventually overcome the elastic ability of the rocks. That's what I just told you right there, right? Kind of like this. So this is the elastic ability. The rocks are the ability to bend. Well, finally you bend it so much, it breaks. That's what it means by becoming overcome there. I want to mention that sometimes that movement is sudden, sometimes that movement is slow. So if it's sudden, that's usually a release of a fairly big earthquake. But there are some places along faults where the rocks are really weak, and it can't, the friction is pretty low, so it doesn't build up very much stress. So the rocks literally just kind of creep along over time. They don't move very quickly, just a few centimeters a year, but those few centimeters a year always build up. And because their rocks are so weak, it doesn't create earthquakes. They just kind of slip and slide along for the whole entire year. But it builds up stress on the other sides of the faults where the not sticky parts are, the non-frictiony parts are. It slides along, but then when the rocks start sticking again on either end of that section, it builds up stress, and that's where you could get some fairly big earthquakes again. So like I said earlier, they're usually heavily influenced by the tectonic interactions of both modern plate boundaries, so the convergent boundaries or the divergent boundaries or those transform boundaries, or it can also be some of those old ancient boundaries like in the Appalachians over here. And they can be really small, like a few centimeters big, these faults, and they can be really large, like thousands of kilometers like the San Andreas. And what I want to show you here in the Midwest or the West, and then like, I guess, Nevada and Utah and all those places, there's tons of faults out here too. And this is because, believe it or not, the continent out here is kind of relaxing and starting to stretch out. It's kind of being stretched out a little bit for reasons that are beyond this class, but just know that it's being stretched just a little bit. All right. So here's what I think I want to do. I want to take a quick break right now. I know it hasn't quite been an hour yet, but I want to take a quick break now. And then when we come back, I want to show you 3 different types of faults. I want to show you how to draw them. And then you guys are going to get into some group work and try to identify this stuff. And then after we do that, then I'll show you the last little bits of how to locate the epicenter of an earthquake, and that'll pretty much be it, be done. All right, so it's 5:17 now. Why don't we come back at, let's see, 5 minutes. So what is that? Like 5:23, somewhere in that neighborhood. So let's come back at 5:23, go stretch, go get a drink of water, check the scores on the games. I know the Giants don't start till like 6:30 or whatever, but we'll be back at about 5:23. Okay, so good job so far and good questions. All right, we've got about 30 seconds or so, somewhere in that neighborhood. Oh. I will say the only side effect of that last booster, man, was my muscles feel all crampy and tight. Like instead of being 6 foot tall, my muscles are made for somebody that's 5'10". They just all feel shrunk. So with that being said, let's take a look at some of the different fault types here. And this will help explain how the Earth moves and explain why it moves the way it does. And then I'll draw some goofy cartoons with you that you guys can incorporate into your drawings, onto your sketch notes. But it'll be kind of a cartoon version of what you're seeing here. So we have three major types of faults. We looked at the faults at the very beginning of the year when you guys were like ordering rock layers, and we could just see how the faults cut across everything. So now we're going to use the angles of those cutting across faults to help us determine how the Earth has moved in the past. So not only like that there was an earthquake, but what types of forces it caused, or what types of forces were needed to make that earthquake happen. All right, so there's three different basic types of faults. And so you'll be hearing on these ones, my friend Wendy, she narrates some of these. She's got the good voice on here. There's a few of the other ones that sound like Toby from The Office, but you'll see. She does a pretty good job.
In a normal fault, the block above the fault, called the hanging wall, moves down relative to the block below the fault, called the.
And so this is the first thing to see. All right. There's two different blocks, and one side is called a hanging wall and one side is called a foot wall. Some people refer to this hanging wall side as a head wall. And the way you can remember this, that's pretty easy, is if I'm just going to I'm going to draw this in just my normal, what do you call it? With my mouse. All right. So I'm going to put a square here, and I'm going to pretend that this is a mine shaft, and that's a person in a mine shaft. So imagine there's a mine shaft that kind of goes down the length of this fault. All right, if you could imagine that. Well, the person here that's in this mine shaft, in order to get light, they would hang a lantern on top or on the side of the fault that is what we call the hanging wall. So this is generally the side of the fault that would like hang over the top of your head, or be the side that you would hit your head on. And maybe the question is, well, Hollister, why are there people digging mines along a fault? And it turns out what the kind of the interesting, really cool thing about this, and I'm trying to find my eraser here, sorry. Where'd it go? There it is. What's kind of really cool about this is when faults break, it loosens up those rocks and it makes the rocks fractured. And when that happens, it allows hydrothermal fluids, so really hot water with dissolved minerals and things in it, to flow up through these different faults. So it turns out that these faults allow mineral-rich hydrothermal fluids to flow up them after an earthquake happens, if the setting's right, if they're nearby like a magma chamber where there's hydrothermal fluids. And when that happens, it deposits them in the fault. And those minerals are things like quartz that have traces of gold and silver and copper and all those precious metals and things that we like mining. They all go along these fault lines here. And whenever there's a big earthquake down at depth, that allows hydrothermal fluids to in place more gold and more silver and things like that. So if you go to the foothills, like all the places that are mining gold in the foothills, they are all mining ancient faults. And that's why they get the names hanging walls and foot walls, because this is the side of the fault where you would hit your head on or hang your lantern on. And then the foot wall, I like thinking of it as kind of like the ramp. So if there was a person standing on this, oops, right here, let's say there's a person standing on either side of this, the ramp is something that they could just walk right up to get off and get out. All right. Or their feet are standing on this. So if this was a tunnel in a cave, right, a mine shaft or something like this, the feet are standing on the foot wall, and the hanging wall or the head wall hangs over your head or goes over the top of your head. So that's how it gets its name. So that's kind of important to know, because once you know the hanging wall and the foot wall, the motion between those two is going to tell us what type of fault it is. So in this case, this is a normal fault where the hanging wall goes down. All right.
Footwall. This fault motion is caused by tensional forces and results in extension.
So in those normal faults, the hanging wall goes down. You pull it apart, it kind of slides down like it's going down a slide at the playground.
In a reverse fault, the hanging wall moves up relative to the footwall. This motion is caused by compressional forces and results in overall shortening.
And this is like, I don't know if you guys ever played on the slides at the playgrounds when you were a kid. Like if you ever tried to push somebody up a slide, that's what happens with these reverse faults. You're literally pushing people together and up and over the slide. And that's what a reverse fault does, is the hanging wall kind of ramps up. And that happens because the forces getting squeezed together. Then
A
Like-
strike slip fault
this is like San Andreas right over here, right?
is a near vertical fracture where the ground has shifted parallel to Earth's surface due to horizontal shearing forces. If you stand on one side of the fault and the block opposite you shifts left, it is called a left lateral fault. If it moves right, it's a right lateral fault.
And so what they mean by that is if I started walking on this side of the river and went and there was an earthquake, and then after the earthquake, the other side of the river is over there, I'd have to turn right at the fault to get to the other side of the river. So that is what we call a right lateral strike slip fault, because it looks like it's moved to the right. All right, when you look across it. And here's the thing, it doesn't matter which side of the fault you're standing on. If I was over here and walking this way, with that, from that point of view, I would still have to turn to my right. If I was walking this way, turn to my right to come over here and get to the other side. Okay, so that's what they mean by a right lateral strike slip, or like you saw earlier, this would be a left lateral. If I'm walking down the creek, bloop, and turn left and go over to there, it's still a left lateral fault. And notice the big thing here too is there's no
If it moves
head wall and there's no foot wall for these strike slip faults. Where is it at here? There it is. There's no head wall or foot wall. These faults are pretty much straight up and down. So if you're like asked to label a head wall or a foot wall on a fault or something, these faults don't have head walls and foot walls. They're just straight up and down. So that brings us to, here's our normal fault. So I'm going to show you this and we're going to draw that little picture. So here it is again. You pull it apart, whoop, down it goes. All right, that's kind of the easiest thing to show. So there's our hanging wall, our head wall, and then here's our foot wall. So what would it look like? How could we draw that? Well, let me share my other screen, and I think you can see my drawing panel now, and I gotta find my pen. Where to go? Here it is. So this is an actual pen. I have an actual digital pen here, so my drawing should be a little bit better here. But we're gonna label this one. I'm gonna get my, oops, thinking, what do you call it? I gotta click on mouse. There we go. Okay, now I can fix things. All right, so we're gonna call this one our normal fault here. So here's our normal fault. And so I'm going to show you the before first and then the after, just so you can have a reference point. So here's our before. I'm going to draw this block with this fault. And I like drawing my cross sections kind of with just a little layer of rock that differentiates the layers above and below it. And then I'm going to put like a person right up here, maybe a tree right up here, because everything needs a happy little tree, right? All the little drawings need happy little trees. So this is before. And in a normal fault, if we have tension, that means we're pulling everything apart like this. What that does is it allows this is going to be the head wall or the hanging wall, which I'm just going to do HW. This is going to be our foot wall like this. It allows our hanging wall to slide down the fault plane, which is this one right here, right? So the after then in a normal fault would look like this. So you kind of draw it like this, and then the head wall or the hanging wall, either one you want to call it, it will drop down. Now, remember, in reality, this is dropping down into, this is going to be dropping down into actual rock. It's not the abyss. But it's just going to cause the rocks to kind of break or slide or move. But what you can see here, here's our head wall. Here's my foot wall. I'm going to use a different color here, hopefully. There we go. There we go. And show you that the head wall has moved down relative to the foot wall. And if the head wall moves down, that's what we call our normal fault right here. Okay, oh, well, I should put maybe I'll put the tree right here. And now the person is green. Okay, so that's our normal fault. That's how you would draw that. Okay, piece of cake. So then for a reverse fault, the way you draw that, let me go back to my other color here.
Are you wanting like in our sketchbooks, are you wanting like detailed drawings or just something like a simple sketch like this?
Just like I'm showing you right now. Yep. I
Uh-huh.
mean, if you want to go make it even cooler than this, that'd be my guess. Make it 3D, make it how like be my guess. But this is kind of the basics of it right here. Yep.
Because I think that's what takes me so long is like I worry about like not putting a lot of detail in it. So it ends up taking me like hours to do the drawings.
Yeah, no. So basics and things here, and you know, you're doing so great already. So don't stress about that. So yeah, I mean, you're doing fine. But the other big thing here is, you know, we're trying to convey ideas. And so, you know, some people can convey ideas with elaborate drawings. Some people can convey ideas with like just even goofy sketches like I've just been doing here. So whatever it takes to convey that idea, that's what we're looking for. And remember, like if I would say, I mean, I'm not saying go for minimalist or anything like that. Go with what works for your mind and how you organize information. And if you want to go to town on it, go for it. Some people just like having the kind of the minimalist details, that's fine too. But if I'm going through and I see some of the minimalist stuff, I'm like, oh, that's not quite enough. I'll just say, oh, hey, maybe just add a little bit here or there in terms of like this is what's missing. And then you can just go back and it's usually, you know, a 2 or 3 minute fix or something like that. So,
Thank you.
yeah, I don't want folks to stress or like I'm not an art critic or art teacher, but drawing and processing like this is one of the ways that helps our mind organize this information and remember this information. And that's why we go through that process. So we'll call this one a reverse fault. All right, so here's our reverse fault. And I guess this one's going to be kind of green. So here's our before. All right. I know what I want to do. I want to show you one other thing too. So here's our pretend rocks. We'll make it so it's kind of the same as before. Here's our tree. Here's our person. I don't know why our person is there. That person probably freaked out if it felt earthquakes like this, but I'm not a good enough artist to show expression in stick figures. So in this case, in the reverse fault, remember these happen from pressure. So compression, pressure, or whatever you want to say. So if you take those two blocks and you push on them and you squeeze them together at like, convergent boundaries, maybe. I'm sorry. If you can read that. Yeah, convergent boundaries. So you have reverse faults a lot. Oops, somebody's coming back in. These happen at like convergent boundaries where you're getting the compressions happening. The after or the result is going to look like this. So we have, oops, I forgot to label this. Here's our foot wall. Here's our hanging wall like this. So the after is going to cause the head wall or the hanging wall, remember that means the same thing, to kind of ramp up like this. So we're going to end up with something that looks like this or something that looks like that on the other side. Here's our tree. Here's my picture of the person over there. And then in this case, I guess I'll use a lighter blue here. Whoop. The head wall moves up compared to the foot wall. So that's the big thing to show here is that this head wall moves up compared to the foot wall in a reverse fault. And that takes compression. And so it literally is shortening and squeezing the ground when we have these reverse faults. This is also what's under, excuse me, LA, Los Angeles, that whole Los Angeles basin. They have a lot of these kind of low angled reverse faults underneath there. It's also at convergent boundaries, subduction zones, places like that. But LA is a big place of where you'd find a lot of these. And I should make mention for this one, for the normal faults, these usually happen at like divergent, can't spell, divergent boundaries. And so because those happen at divergent boundaries or places that are pulling apart, it leads to extension of the Earth. So literally the Earth's crust, I'll just say the extension of the crust, the Earth's crust, point A to point B, gets farther apart from where it started. All right. So like if this is the before, the distance between this person and this tree was maybe, let's say, 100 feet. All right. After this earthquake, the distance between this person and this tree would maybe be like 103 feet or something like that. After one earthquake, it slowly steps away, or it slowly gets further apart. All right, so it extends or gets a little bit further apart. So same thing here. If this was 100 feet between the tree and the person over there, after a reverse fault, it would shorten things up. So no longer would it be 100 feet, maybe it would be like 95 feet between the person and the tree after that earthquake happened like this. Okay, so that's a reverse fault. And then the last one, we have our strike slips. And so for our strike slip faults, we have a couple of ways of looking at it. We're going to say, here's our before, and I'm going to use train tracks here. Okay, so I'm going to look at it. I'm looking at it from above, like I'm an airplane flying and looking down, and here's some train tracks going across the country. So here's our before. The after then is going to look a little bit like this. So, oh, I should mention, these happen because we have forces that are kind of pushing in opposite directions on either side of the fault like this. So if we have arrows pushing like this, it's going to move the top block over like so. All right. And what that's going to end up with is our train tracks looking like this, right? Let me see here. Oops, wrong way. Got my diagram messed up here. There we go. Now it's the right way. Well, let me make it a little bit more obvious here. Let me try this. Give me a sec. I want to make it so it's nice and not confusing. All right. So we'll pretend they started out together. Now they're offset. And what we call this then is after this motion, if this one's going that way and this part's going this way, if I start on my train track path here, let me get a different color. If I start on my train track path here and I go up to the fault and go across the fault, I have to turn to my left. And so we would call this a left lateral strike slip here. All right. So I'm just going to leave that at left lateral. And then the opposite version of this would be a right lateral, which means we'd have an offset that looks like this, where we have our train tracks in the middle. Here's our other train tracks over here. And if I went from this side, across the fault to get to the other tracks, I'd have to move to the right. So that would be my right lateral. All right. So that's how you tell all these different things apart. And it's a really big deal in geology because it helps tell us the past motions of the earth, or whether things are being squished or pulled apart or moved side by side. And if we can know that, then we can totally know and understand, what the hazards are, what the threats might be when we are trying to assess what's going on where we live. All right. So let me go back to my other screen here. So those are our normal faults that I just showed you. Whoops. I do want to show you a couple of other examples in the real world here. Let me see here. Those are, yes, exactly. Sorry, I did not see the chat. I just saw the chat come through right now. I was on my other screen. So yeah, for the strike slip faults, there's no head wall and there's no foot wall, just like Wendy and Zoila said. So yeah, you guys did great, or Wendy said, you guys did great there. Good job. So these normal faults, like I said, happen when the earth is pulling apart, the head wall moves down or the hanging wall moves down, happens at divergent plate boundaries. But check out these little videos Like if we were in person, I'd bring in some of these and we'd kind of experiment with them in person, but there's some cool videos of it too, of these sandboxes where you can, this is literally how geomorphologists and seismologists, we study the motion of the Earth's crust. We play with sandboxes and we do experiments to see things, how they move over time. But you can see, like if I rewind time there, everything was in one layer. And as it starts extending and stretching, you can start seeing all the different, all the normal faults that start forming right there where the head wall is moving down compared to the footwall. And then this footwall becomes the other head wall to this one, which is kind of crazy, right? So we have all these different normal faults that start extending. And in Eastern California, the basin and range, this is where you find that stuff. And here's a quick little video to show what that looks like. So if the crust in the eastern part of California starts pulling apart and extending, this is what will happen over, this is what will start happening over time. So I don't, oh gosh darn it, I'm trying to pause it and it keeps doing this funny thing here. Give me a quick second here. So this is over millions of years, right? So the blocks go down and then the mountains erode. And as they erode, they start filling in the valleys below. But if you've ever driven up to the Sierras, like if you drove to Tahoe, you know, it takes like 2 or 3 hours to get up over the Sierras, over the passes to get to Tahoe or to Reno. But then once you get Donner Summit or you hit like Echo Summit, it only takes like 20 minutes to get down to the other side. And that's because the eastern parts of the Sierra are right along a huge fault, a normal fault where everything else is sliding away and going away that way. And what's kind of cool about this is you can really see that. I need a quick drink of water here. You can really see that in the satellite images in the Basin and Range province between, like, let's say the Eastern Sierras all the way out to, say, Utah. And every single one of these mountain ranges here is literally just a tilted block of old continent that has slid down. It's this normal faulting. And so this part of the mountain range, that's the footwall. And then this part has slid down. This is this would be the head wall sliding off of this footwall. And then this part over here would then be the footwall for the head wall over here that has slid down. And give it enough time, it stretches and extends things. And the distance literally between Reno and Salt Lake City over the last 5 or 6 million years has, we think, almost doubled. It would have taken half the amount of distance traveled 6 million years ago, but the crust is extending for some reason here. And like I said, that's kind of beyond the scope of here, other than to just know it's extending for right now, okay? So then we have our reverse faults. That's where you push it together, boop, it goes up. I think you guys are pros at this now. We drew it everything, but I just want to show you that's a reverse fault that goes up. And we can see this happening in these little sand table models as well. You can see the layers that are right here, the original layers. And as it starts squeezing the layers, we're compressing the layers with a little vise. The layers get thicker. And then after they get thicker, they finally start sliding up over on top of one another. And you can start seeing the definite patterns of this reverse faulting happening here, where the head wall is going up or the hanging wall is going up over the footwall, which is pretty nuts to think about. We can model this really well with just like flour and sand and things like that. And it does a really good job providing an analog to the real world. And then there's the strike slips, like I showed you. And one thing I just want to make sure that you all know is sometimes those strike slip faults, even though the San Andreas fault runs right through here where my arrow is pointing, sometimes those faults like the San Andreas get a little kink in them and they don't run exactly in a straight line. They kind of kink and then go again. Well, where it kinks, it allows for what we call transpression. And you'll see that happen here in this little video clip. I think it'll play, there it is. So the fault keeps moving along, but that transpression, or basically kink, causes things to get kind of mushed up and smashed up and built up over time. It creates little hills. And if you've ever driven to Southern California over like the Grapevine on I-5 down into LA, The whole reason the transverse ranges are over here is because of motion like this along the San Andreas Fault. It's a strike slip fault, but there's a little kink in it, and that kink is causing the rocks in between to be pushed up to create the transverse mountain ranges that are right here. And it also creates some of those other reverse faults that are down in the Los Angeles basin, which is kind of interesting and neat to think about, well, I think anyways. So we know right and left lateral strike slips. Here's an example from the Ridgecrest earthquake in 2019. My geology friends that work for USGS and stuff, they got to have the chance to go fly in helicopters and look at this stuff right after it happened, which is amazing. But this is just to show you, it's not supposed to be a guy falling out of a helicopter. Somebody said that in one of the other classes. That's not what this is. It's supposed to be a person walking down the highway. And if they had to walk and cross the other side of the highway, they would have to cross the fault and then go to the right to get to the other side of the yellow line right there. So this is literally the fault that ruptured in that earthquake in Ridgecrest going right along here. And you can see that it offset that entire road by a good 2 or 3 feet or something like that in one earthquake, which is pretty cool. And it's a right lateral offset. The other version here is Wallace Creek or Wilson. Did I say Wilson? Yeah, it's Wallace Creek. I don't know why I said Wilson in this one, but check this out. It's a beautiful, amazing place. I'll show it to you here in Google Earth. Hopefully it'll fly into here in just a quick second. I should have this one loaded. But while this one loads, what I will say here is that in the springtime, when it rains, when there's a good rain, the wildflowers are just nuts. And it looks like somebody's just dumped buckets of paint all over the mountains. The wildflowers are just so gorgeous here. But here we go. Come on. There we are. There we are. This is Wallace Creek. The San Andreas Fault is right here. And if I go like this, you can kind of see that big line running right down the middle. That's the actual San Andreas Fault, believe it or not, that you can see right here. So this is over by San Luis Obispo, just outside of San Luis Obispo. But Wallace Creek is an offset stream that flows down from the mountains in the springtime. So I'm going to kind of go like this, flows down the mountains, and then would normally go out into what we call Soda Lake out there in Carrizo Plain National Monument. But the San Andreas Fault, right, it has had other plans the last few thousand years. The creek 5, 6, 7,000 years ago used to be right over here, and the creek flowed straight across the San Andreas Fault. But in the last 5 or 6,000 years, there's been multiple earthquakes that have taken this creek bed right here and made it move over to the right. So this is what we call a right lateral fault, because if I go down the river and go across the fault, I have to turn to the right to go to the other side. And just to show you that it doesn't matter which side of the fault you're on, if I jump over to the other side of the creek, well, look at this. If I follow the creek up right here, well, look at that. I still have to go to my right and then go upstream like that. So it doesn't matter which side of the fault you're on, it's a right lateral fault. And if you decide to take other classes like this, or want to go on some other cool field trips, the San Andreas Fault down here, there's tons of amazing places to see, like different landforms, and just it's the San Andreas Fault out in the middle of a desert, and you can see all these amazing like shutter ridges and all sorts of cool stuff that's out there. But anyways, I digress. So that's a right lateral fault. So now here's what we're going to do. We're going to get together. We're going to have a little bit of fun here, and hopefully we're going to identify some fault features. So let me see here. I'm going to copy this and I'm going to paste this into the chat. Everyone, there we go. All right, and I think y'all should be able to open this now, and I'll show you what you're going to do. All right, I see a couple people there. Let me make sure I'm having it on the right presentation thing. Oops, let me see here. Yep, anybody can edit it. So in your groups, a quick drink there, sorry. In your groups, what we're going to do is we're going to spend probably 20 minutes or so. And you have 4 slides for each group. And what I've done is I've color coded like every 4 slides or so a different color. So group 1 is going to be like pink. Group 2 is like this beige or whatever. Group 3 is green. All the pictures are the same in all the groups. It doesn't really matter. All right. And so you're going to get into your groups, and then you're going to use in the slides here, you're going to use the pen or the line tool, and they're no pen tool anymore. So it's just going to be the line tool. You're going to use a line tool to trace the fault in these pictures. So find the fault, and you're just basically going to put a line on it. So you can start it at one place and then go down and drag it, and oh, hey, there's the fault. If you want to make the line bigger, this is the thing you click right up there. You can make it like 3 point, 4 point, whatever. You want to change the color, make it so it's easier to see. You can click on the color thingy and make it whatever color you want. So there's my fault. That's step one. Then it says label the head wall and the foot wall. All you got to do is just type in HW for head wall, and then FW for foot wall, like this. And then your group will have to figure out, oh, which side is the head wall, which side is the foot wall. So here's a person for scale. Here's kind of the side that looks like it's hanging over it. Here's the side that looks like maybe I could use as a ramp to walk out. So once you figure out which side is the head wall and which side is the foot wall, you put the labels on there. So this one is kind of a freebie for everyone, especially group one. All right. If you want to make it so it's easier to see the text, you can change the color too, or just put it in an area where it stands out. Then it says draw arrows next to the fault to show which direction the head wall has moved. So just use one arrow to show which direction the head wall has moved. And in this case, if I look at this brown or gray piece of layer of rock compared to this gray section of rock, it looks like it's moved down. And so I draw my arrow. I'm going to make it so that it's easier to see and make it just a little bit bigger. And so my head wall has moved down like that. So if the head wall has moved down, that will help us figure out, is it a normal, a reverse, or right or left lateral earthquake fault, right? So remember, the head wall moves down. What does that make it? You'll have to think about it and talk about it in your group, okay? So head wall moves down. If then you think that it's moved down and that it happens to be a normal fault, which is the case, the last thing I need you to do is just take two arrows or an arrow like this, and I need you to make two big arrows. So I'm going to make this like 12 point or something like that to show the basically what it took to make the fault do what it did. So in this case, to make it a normal fault, the rocks were pulling apart, which allowed this one to slide down to become, in this case, a normal fault. So you can just put normal. You don't have to put fault or anything. We know we're talking about faults. So that's how you do it, just normal like this. So you talk about it, try to figure it out, label it. Same thing with this one. Oops, somebody's coming back. Good. You can put the fault across here. This one, my wife is sitting in the picture in Death Valley, so it's easier to see. You can notice where her head is and where her feet are. That should be a clue for that one. For this one, I already kind of drew a fault in there that's kind of hidden, so you can make this one a little bit thicker, but it should help you figure out what is what. I will also make mention that this layer right here and this layer right here used to be the same thing. All right, so this layer and this layer were the same layer. Here's one in Arches National Park. And then for this one, I'll tell everybody right now. So I just want to kind of help you remember. For the third slide in your group, these two pictures right here, these are overhead shots. These are both strike slip faults. All right, you just have to tell me if they're right or left lateral. So still draw the line across, but there's no head wall, there's no foot wall for this. Just tell me if they're right or left laterals. This one's from a New Zealand earthquake about 6 or 7 years ago. And then this is a mountain range in China. And you can see the scale here. This is from the sky looking down, like satellite view looking down of this beautiful eroded mountain range in China. That's 2 kilometers. So from one side to the other is probably, I don't know, what, 25, 30 kilometers, somewhere in that neighborhood, right? So it's a pretty big distance here, just to think about. So that's all we're going to do in the next 20 minutes. If we get to this one, you can try giving this one a chance to, but my guess is this is kind of where we'll end up is after slide 3 in about 20 minutes. And just see what you can come up with, labeling these faults and trying to figure out what types of forces acted on them to make it happen the way it did. All right. And so we'll have fun with this. We'll do like probably, I'll put the breakout rooms for 15 or 16 minutes here. Let's do 16 and we'll go from there. So we have 5 groups of 3 and We'll do 15 minutes or so, and we'll see what we can see and see how well you do in that amount of time. All right, so here we go. I'm opening the rooms and go for it. All right, I think everybody's back. I keep forgetting I have it set on the 10-second comeback thing. Yeah, you guys, great job. I mean, this is the first time you've ever done this, so kind of a low stress way of trying to figure out how this goes. But for the most part, everybody did really well, right? So and I'm not trying to pick on this group or anything, but I'm just going to see some good examples here. Everybody had good examples, but this is indeed a normal fault like we talked about. This one over here was also a normal fault as well. You can see my wife's head is on the head wall, her feet are on the foot wall. And what kind of threw some folks, like if it went up or down, I think they were like looking, I don't know, I'm not exactly 100% sure, but the layer that really, I think, shows what used to be connected is kind of this dark red layer up here. And that red layer looks like it's slid down that fault if you're looking at it. So because the head wall went down, that would make this a normal fault, which they got going on here. For sure. For this one too, definitely a reverse fault. So this layer and this layer used to be the same, which means that layer had to move up. The head wall layer moved up compared to this layer right here. So it started here and moved up to there. And so in order to do that, that gets our compressive forces, definitely a reverse fault. I know this one could be a little tricky because there's so many different layers of like brown and white in there that can kind of throw you off in terms of which direction it goes, but that's good. And then at this one, for the normal fault, a lot of folks, I saw it in multiple groups here. Like the fault is there. It's totally great kind of going through this section, and there's like more than one fault, right? There's a fault here and over there. But on the big picture, yeah, the fault is here. And you'll notice that this big chunky, wide chunk here of like pinkish rock used to be this big wide chunk of pinkish rock up here. So it has slid down compared to this one right there, which means it's a normal fault and it's pulling apart. If you ever get a chance to go to Arches National Park, this is right outside the park gate, and you can go right across the street and see some of these big honking faults right across the way. And so for this one, I know not everybody got to these, that's totally fine. But our faults for this one, I'll just kind of add one so folks can see stuff here. If we drew a line from like there to there, this is definitely the fault. This person's house was built right on a fault, it turns out. And before the earthquake happened, their house was over here and their driveway used to be connected, but now it's not. So if I go across the fault, I'd have to go to the right to find the rest of their road. And that's definitely a right lateral. And if I go to this one in China, and I know the fault right here is kind of running, oops, not that, going right this, like right down the middle. If I start on this side, I have to go across the fault to the left to find the rest of the mountains on the other side. So this would be a left lateral fault. So you all did excellent, and I'll show you the other one here in just a second in Death Valley here. And so you guys did such a good job. This is a right lateral fault, by the way. This is me over in, it's a winery over by Pinnacles National Park that we stop at, because the San Andreas Fault runs right here, right through there. And you'll notice the water on this canal ditch tried to go straight. The ditch was straight when they built it, but in the last 100 years or so, over to the right and down it goes. So this is definitely a right lateral fault. And you can go stand right on the San Andreas Fault if you want to, and you know, go visit a winery as well, but just not on the geology field trips. We see the winery because it's being ripped apart by the fault. So you guys did that. And then kind of the bonus one that I know we didn't have quite enough time for. This is something we always stop at in Death Valley. And so right on the outskirts of Death Valley, we see this fault. Here it is right there. There's me going, okay, is it a reverse or a normal fault? And what's pretty awesome about this is most textbooks that have this picture in there of this fault, they list it as a reverse fault. And they list it as a reverse fault because everybody's eyes kind of key in on this like orangish band right up here and this orangish band down there. But that would make it a reverse fault if that were the case, because this would be the head wall, and this would be the foot wall over on this side. You can see the angle of it. There's the hanging wall hanging over the top of my head there. But if you give it a little bit of a critical look, it turns out that this is not the same thickness as this stuff down there. And if the light were better, what you'd be able to see is that there's this kind of white layer of tephra right here, which is the volcanic ash, right? There's this white layer of tephra that's right in there. And it has actually been offset and gone down. And so the hanging wall in this one has actually gone down, which means this came from a little bit up higher and slid down. So where, if I asked you then, where on this side of the fault, on the hanging wall side of the fault, where is all of this orange and yellow and brown stuff that's right here? Where would I have to go to find this stuff? Like in this picture, like where would I have to go over here to find the other matching bits?
Is it
Oh, not quite at
top?
well, if I went to the top, maybe, but if you take a look at this, so if you imagine these black layer, the layer I have highlighted here, if you imagine and rewind time and bring the hanging wall, let me maybe get my pencil, that'll help maybe. I'm sorry, trying to find my pen. There it is. All right, let me get a better color here. Okay, so in this case, here's our head wall or our hanging wall. Here's our foot wall. All right, there's our foot wall. And in this case, the hanging wall has gone down. That's supposed to be a down arrow. It's moved down. And we can see it's moved down because this layer is now down compared to this layer right here. So if this layer is underneath the black layer that I have highlighted, where would it be over on this side? It's still going to be underneath it. So where would I have to go to find it? Right? Yeah, you'd have to dig it, and you'd have to dig underneath right here. So if I were to get an excavator and start digging the rocks away right here and clearing out all the stuff and digging down 5 or 6 feet, I'd find the other side of these rocks right over there on this side. So that's kind of a cool fault to be able to see. And it's because it's a normal fault, we would expect to have extension there, meaning it's being pulled apart. And as luck would have it, I just happened to fly exactly over this spot. I put some arrows on, I forgot, I didn't need to draw. But what happened is I flew right over this spot a few years ago, flying to like Phoenix or something like that. And I was able to take a picture, and you can see kind of these Basin and Range mountains here where we have all these normal faults that cause this extension that's happening down out in the basin and range in the Mojave Desert and stuff. So that's where I took the picture, right on the road, and I flew over it and I was like, oh, that's exactly where I was just at, which is kind of cool. All right. So how about this? Here's a strike slip fault. There's the actual town of Hollister. You know, you can say I have my faults, but so does the town. And here's the San Andreas fault that run, or excuse me, the Calaveras fault that runs right through the middle of Hollister here. The rocks in Hollister underneath are kind of weak, brittle, more like a serpentinite and other metamorphic rocks that just don't have very much friction on them. So here they don't have big earthquakes. This is a place where the fault just kind of slips along. And if I follow this fence and assume this fence was one nice straight line 80 years ago when they built it, what direction has the fence moved? If I'm standing over here and I look across, the fence is moved to what direction here? Across the fault. Like if I look across the red line, it looks like it's moved to the, well, I guess I'm mirror imaged, but it's moved to the right. And so this is also a right lateral fault running right down the middle of the town. And I look like I'm trying to pull the fence there, but really this helps us understand exactly how fast the fault is moving, because when it was a straight, nice fence, it's now been offset by like 3 or 4 feet in the past 80 years. And so if you do 80 years, 3 feet divided by 80 years, it'll tell you how many inches it moves on average each year as it slides by. And you can see the sidewalk too. The sidewalk used to be straight, but it jags to the right before you keep going down the street. And all the streets in Hollister where the fault runs right next to and through are offset. So here's the curb, you have to jog to the right and then go straight like that, right? Like a zigzag over there. And some houses are unfortunate enough to be built right on top of the Calaveras fault in Hollister. And so here's their foundation, whoop, right laterally offset. So, you know, after 30, 40 years, their foundation gets really starting to get offset. It can mess up pipes and all that other kind of stuff. So they have to come up and figure out ways to make sure their house doesn't get ripped in half over 100 years worth of time. So maybe they have to cut things open and, you know, redo the foundations and relieve the stress. Because if they didn't, their house would eventually split, just this slow motion, like, excuse me, like a vice pushing on all directions, right? So probably not a house you'd want to buy in Hollister. And then if you know Berkeley, Cal Berkeley, the football stadium in Cal is built in Strawberry Canyon, and the Hayward fault, which is a right lateral fault, runs right through the middle of the stadium, like almost goalpost to goalpost. And if you go to the top of the stadium here, the stadium wall has been offset, you know, like almost a half a foot or so in the 80 years that, or 90 years that the stadium's been in existence. So back in like 10 years ago, they just did a huge stadium renovation and they literally split the stadium in half. So there's 2 separate parts. It doesn't connect anymore. That way, if there's a big earthquake, the 2 pieces of the stadium can slide perfectly by one another. And it's kind of cool. If you go down on the field on the AstroTurf, they actually have a jagged piece of AstroTurf to show where the fault is. And you can see it if you watch games like that, but it's just kind of a funny thing. It's not going to be so great if there's a magnitude 7 that goes there anytime soon, but you never know. So just to kind of, I just want to get your brains wrapped around of where kind of these major different faults are in California. Now that you know how to identify them and what they look like and stuff like that, here's kind of the 7 major named faults in California that we pay attention to. Obviously, the red ones here mean they're a greater risk or greater probability of having a large, like magnitude 7 earthquake or greater on it in the next, you know, X amount of years. This is just where the rocks have the most stress and strain built up on them. And we know that based on geological surveys and putting meters in the ground that can measure that stress and strain. We can dig trenches across the faults and figure out how many times it's moved in the last, you know, 1,000 years or so using carbon dating and different layers across those faults. They can figure all that out. And once they do that, this is what they come up with is the Southern San Andreas fault. This is kind of the oh crap fault in California, where there's just a lot of strain and stress built up on this thing. And, you know, if people were betting, if geologists were bettors, the probability of having a very large earthquake down here before anywhere else in California is just about as good as happening along the Hayward Fault, which runs through downtown Oakland, Berkeley, and like Napa and places like that across the bay. So both of these have equal amounts, but really the southern San Andreas down here and parts of the Elsinore Fault down here are just, these are the ones that we're most concerned about. And they happen to run through hugely populated areas. So, you know, the more we can offset those problems, like build things that don't collapse and make sure we have ways to stay safe, we'll be able to get through it here. Okay. So with that being said, I'm gonna let's see here. Yeah, 6:30. Let's just take a, well, let me ask you guys. Do you guys want to take a quick little break, or do you want me to just kind of jam through it? I'll ask you really now. I'll give you the choice.
I think you should continue.
All right, we'll continue. Either or whatever. All right, we'll continue, and then maybe we'll get done a little earlier so we can see more Giants Dodgers, right? So we'll see. All right, so here's the causes of the earthquakes, and let me make this bigger screen. I just realized this was not so much. So I mentioned it on it earlier, and I'm not going to like harp on it too much. How strain builds up on the earthquakes, and back in the 1906 earthquake, that was the first realization that geologists had that, oh, this idea that rocks can bend and store energy, and then when they break, that release that energy and kind of go back to normal. And they came up with a name for this process called the elastic rebound theory. And that's kind of how we still operate today. And how we know the Earth operates today is that if you have that fault running through the ground, over time, that stress and strain builds up. It bends the rocks and it literally loads those rocks like springs. It's like pushing a spring tight and holding and storing all that potential energy until the fault can't hold that strain anymore. It ruptures, it breaks, and it sends the energy out, just like a ruler, if you had a ruler and broke it. And the kind of really famous example is when I did teach high school, we had lots of, I'd take a club out and we'd go adventuring all over the place. And this is at Point Reyes in San Francisco, like 15 years ago. But this fence used to be together. The San Andreas Fault runs right where everybody's standing right here. But this fence used to be together, and it moved that entire distance in the 1906 earthquake, which is like 13 or 14 feet. So can you imagine being here and watching this over a 2-minute period of time, the whole earth just shaking and sliding and moving past, and when it's done, everything on the other side of you is, 15 feet further away. And it'd be so crazy to think about. But you'll notice the fence is straight, and the fence is straight over here. Is once it releases that energy, the rocks kind of go back to being straight and undeformed until more stress or strain is applied to them. And so if you think of the San Andreas Fault as kind of like bricks of rock that are kind of highly friction and stuck together, and you think of strain as being stored up as like a rubber band or like a bungee cord, I want to show you kind of a model that explains, or I think kind of helps demonstrate how the earth and earthquakes build up stress and strain over time, and then the earthquake happens and releases that energy, but then also puts some extra strain on other pieces of the fault. So let me just, I think that was a poor description. So let me play it to you and just kind of set up everything here. Imagine these blocks of wood as being like the North American plate of North America, all right? And imagine this sandpaper down here as being the fault, and the table that this is on is supposed to be like the Pacific plate or something, all right? The Pacific plate. And these blocks are trying to slide past one another. So what you see here is each one of these blocks has a rubber band attached to it, or a bungee cord, and you'll see that it takes a lot of extra strain to finally overcome the frictional forces that are holding those bricks and those blocks together. So stretch, and you'll see, finally, that was enough to move this block, which in real life would be an earthquake. So that strain finally overcame the friction there, which made the small earthquake. But watch what happens to the bungee cord between these two blocks over time. Boop, another small earthquake. Then boop, another kind of bigger earthquake there. But you'll notice as these earthquakes are happening, it's lengthening out or putting a lot of strain or loading this bungee cord right here on the rock behind it. So this is every small earthquake this one is having, it's now putting more strain on the pieces of the fault that are behind it, and then also on the pieces that are in front of it that it's smashing into eventually. So this is releasing the strain, but it's building more energy there. And then woof, you can see down it goes. And then this one creeps along its way, creeps along its way, creeps along its way, and then boom, there it goes, right? So this one probably had less friction than this one. This one had more friction on it, which means it built up more energy over time. And this is how the San Andreas Fault works. If you go down by Pinnacles National Park, it kind of creeps along just like this, a lot of small little kind of almost imperceptible little quakes. And then the other parts like the Southern San Andreas and the Northern San Andreas, they're more locked and it takes way more energy for them to break. And because it takes more energy for them to break, when they do break, they make big earthquakes. So I'll skip this one. That's Parkfield. It doesn't really matter. You don't need to see that one. So where do we see these earthquakes? Here's a couple little bits of terminology here for you then. The epicenter of the earthquake is the place on the map where the earthquake happens. But in reality, the fault actually ruptures somewhere down deeper in the crust. It rarely ever happens right at the surface. So if we say, oh, there was a 6.9 in San Francisco, it was under San Francisco. And so the epicenter is up here, and then the focus, or what we call the hypocenter, either one of those words works totally fine, is the depth, the place where it actually happens. So the epicenter is the place on the map, the focus is where it ruptures down below. And when we were looking at those seismic viewers earlier, basically like when we were doing the plate tectonic stuff, everything that's in here, each one of these dots, those are epicenters. That's where they happened on the surface of the earth. Like if we triangulated them, that's kind of like the spot that it was over. But if you click on those, each one of those colors has a specific depth to them, or each one of those earthquake epicenters that you see here has a depth to them. And if you do the cross section, you can see that these epicenters also have a depth to them. And if you draw a line straight up, boop, that's where the epicenter would be on the surface. If you went up and drew lines straight up, boop, that's where the epicenter would be. So this is what we call the focus or the hypocenters. The epicenter is kind of their expression on the surface of the map. So we're not going to do a Jamboard with this, but what we are going to do is, just for time's sake here, what we are going to do is we're going to watch a quick little simulation, because now we're going to talk about the different waves and how they can travel through the earth. So this is a cool little simulation that you can click on it. It's also in the modules here. But what you see is literally the earth cut in half, and I'm going to choose a different earthquake. Let's see here. Let's see, what earthquake should we think about? Let's see here. Let's do like the Loma Prieta back in 1989. That's one we know. Let me do this. Boop. Okay, so we're going to load the quake. And now you'll see we have this half of the earth. We have each one of these funny letters right here. This is a seismic station that actually records seismic waves, right? So the jiggles, the things that makes, it's the seismometers that makes the jiggles that you see in earthquakes. And what we're going to see is we're going to have the earthquake happen. Here's its epicenter or its hypocenter, its depth. And I want to see how these different earthquake waves travel across the globe. And I'm going to turn off the sound because it's annoying, but I'm going to go start. Boom. Okay, there's the earthquake. And you'll notice we have a couple of waves labeled here. We have P waves, we have S waves, and then we have our surface waves. And I want you to just kind of notice and wonder what are some characteristics you notice about the P's and the S waves as these keep going through here. I thought I turned the sound off, but whatever. All right. So some of the things that I notice, ooh, look at that. Some of the things that I notice is those P waves are definitely kind of traveling faster than those S waves, and the P and the S waves both go through the earth, and then they start bouncing and reflecting around. And if I go over here, let me reset that so you guys can see it again. If we go on the surface of the Earth, look at that. Here's those P waves, here's those S waves, and then here's the surface waves. They go rushing out, and every time they hit a new station here, you can start seeing the seismic waves showing up on these stations over there. The P waves, you'll notice they're super fast. They always hit the stations first, and then the S waves come next, and then the surface waves come a little bit later than that, right? It takes a lot longer for those waves to hit the other side. So that's something to think about. The P waves, oops, somebody came, that's nice. The P waves and the S waves, they travel through the Earth, but they can also be felt on the surface. And then the surface waves, they just roll and travel and roll across the surface of the Earth. And we're going to see they do some damage later on. The other thing I want you to just kind of notice just really quickly here is that the P and the S waves, watch what happens when it hits the core of our Earth. All right, the P waves, they keep coming on through. Some of it gets reflected back to the surface, but watch what happens to these S waves. The S waves, they really don't travel through. The original S waves, they don't travel through the core. And that's how we know the core is liquid, because we know that these types of waves that the S waves are, they cannot travel through liquids. And then it makes like a shadow of them on the other side. And that's how we're able to figure out that the outer core is liquid and the inner core is liquid. And it's how we were able to figure out the different layers of the mantle, is by how all these waves bounce and reflect off one another. So if you're into math and geophysics, you can use all this information to basically make like a sonogram for the Earth to be able to tell what's on the inside of it, which is kind of cool. All right, but I just wanted you to see here, the P waves are fast, then the S waves come, and they literally are really, really, really fast. And so let me show you how fast they are here. All right, I'm going to skip this one. Where'd we go here? Oh, no, I'm going to show you this one really fast. I forgot. So this is showing you how we record the different waves and how it would feel to us on the surface, okay?
Earthquakes produce different types of seismic waves that can be identified on seismograms. But did you know that each seismograph station produces 3 different seismograms for each earthquake? What
I don't know why I keep stopping this. Hold on.
seismograms for each earthquake was? Earth's movement is 3-dimensional, and one component only reflects one direction of movement. If a station had only one component, you would only know about movement in one direction. Different instruments on the seismograph measure 3 types of motion: up-down or vertical motion, north-south motion, and east-west motion. Let's take a close-up, exaggerated look at how a house would be affected by each direction of motion. When the house is shaken in the east-west direction, this shows up on the lower component. Nothing is recorded on the north-south or vertical components. When the house shifts north-south, this shows up on the second line. When the house is shaken in an up-down or vertical motion, only the top seismogram records the motion. During an actual earthquake, the house can move in all directions. Why is that? Earthquakes produce different types of waves, like body waves and surface waves, and these waves travel out from an earthquake in all directions. Body waves, like P and S waves, travel a curving path through the Earth. As a result, they arrive at seismic stations from below. P waves are compressive waves that cause temporary microscopic deformation of the Earth in the direction the wave is traveling. Thus, energy is primarily recorded on the vertical component of the seismogram, with less energy recorded horizontally. S waves move more slowly and are more destructive since they advance with a shearing or back and forth motion. Because S waves arrive later than P waves, they're usually seen on a seismogram as a second pulse. S waves cause deformation perpendicular to the direction of wave travel, which is primarily horizontal or back and forth motion, with less energy recorded on the vertical or up and down component. The slower surface waves, such as Love and Rayleigh waves, move in a more complex undulating pattern and thus show up on all 3 components.
So I'm going to show you that, but what's kind of cool about this is the seismographs, the modern ones, this is how they record all these. But I want you to notice the P waves are always showing up first, And then the P actually stands for primary, S stands for secondary. And so the S waves come out a little bit later, and they generally have higher amplitudes than those P waves. And what we're going to see in just a minute here is the distance between the P, or not the distance, but the time between when the P wave hits and when the S wave hits, those differences in times, that can help tell us how far an earthquake is away from a seismic station. And that's going to be important to figuring out where earthquakes are. All right. So for those body waves, like I was showing you, oh man, I hate how it does this. There we go. For these seismic waves, those body waves, the P and the S waves, they're the ones that travel through the core. And here's that shadow zone I was mentioning earlier where the S waves don't really travel through. And then we have the surface waves, the Rayleigh waves and the Love waves that roll along the surface, just like you guys saw. And I have a few better little demonstration animations to help you understand how this goes. But to give you a few facts about P waves kind of move like an accordion, like this back and forth compressional wave. They're fast, 13,400 miles an hour, right? That's super fast at the surface. So they're the fastest, they're the first waves that reach the surface in an earthquake. S waves, they're the slower waves, they're the secondary waves, but they're still screaming fast at 8,900 miles an hour. They're just, they're just about half the speed of P waves is all. So they kind of move up and down. Like if you ever played jump rope and you did like a snake with the jump rope and made it go up and down, that's how S waves move. All right. And the other big thing about these S waves is they cannot travel through liquids, which is why they get absorbed in the liquid core and don't show up on the other side, depending on where you're at in the earth. So those are our P waves. They go first. S waves come second. Here's a good demonstration to kind of show you how those P waves microscopically move things in the earth or compress the earth as it moves through like that. So that's a P wave. Over here is an S wave. It's kind of like the snaky motion right here, kind of going up and down. And or like the dance move. I can't do it really good. It doesn't even show up very well, but moving your arms like that, right? That would be like doing an S wave. If we were in class, I'd be having you dance and stuff like that, but I'm not going to put you through that here. But what's kind of cool here is because the P wave travels faster than the S wave, to give you an analogy of like a racer, I ran track. So when I was in college and high school and stuff, I ran track and I was pretty fast. I was a sprinter and a jumper. But if I was to run against Usain Bolt, who is the world's fastest person ever to live, 100-meter champion, if we both lined up at the starting line and the gun went off, we would finish that 100 meters. He would probably beat me by about 10 yards, right? Or 10 meters or so in that 100-meter race. He's just screaming fast. However, if we were to race at that same exact speed, if we could maintain that exact same speed, racing around the whole 400 meters of the track, right? He'd still be going way faster than me the whole time. So over 400 meters, he's going to cream me even more. Even though we're both running the same speed, he's probably going to cross the finish line 50 or 60 meters ahead of me. And that's what happens with P and S waves. The farther you get away from where the earthquake happens, the epicenter was, or the hypocenter was, it gives more time for the P waves to get out in front of the S waves. So what happens is if you're in a place really far away from where the earthquake happened, when the S waves and the P waves start hitting your seismometers, there's going to be a much longer time period from when the P wave hits to when the S wave hits. If you're closer to the epicenter or the hypocenter, there's going to be a shorter amount of time between when the P wave and the S wave hits. So that time difference tells us how far away we are from the earthquake epicenter, kind of like this.
Seismic waves, including
this is the guy that sounds like Toby from The Office. It's so funny, but anyways.
And S waves carry energy away from the hypocenter in all directions. The P wave propagates with particle motions that are parallel to the direction of propagation. It has a velocity of about 6 kilometers per second in rock. The S wave is slower at 4 kilometers per second and propagates with particle motions that are perpendicular to the direction of propagation. While both the P and S waves are generated from the same source, the faster P waves travel ahead of the S wave. Because of this speed difference, the further these waves travel, the greater the space between the two becomes. When we record these waves, The gap between the P wave and the S wave provides information about how far away the earthquake occurred from the seismograph.
See, they explain it so much better. So those are P or S waves, and then the surface waves are the Love and Rayleigh waves. And I think it's better showing them like this. So the Love waves are kind of like a back and forth, but like kind of anchored on the bottom, like a snake kind of moving like that side to side, but anchored on the bottom. And then the Rayleigh waves, they're more like an undulation like you would experience on a boat in the ocean, how they kind of just roll. And my goodness, this is the thing I remember the most from the earthquake in 1989 in Turlock. I mean, our streets were just, yeah, it was like if you got seasick, it was not a fun time. So that's what I remember. All right, so that brings us then to the seismograms. So the seismograms are the squiggles that we were talking about, and the P waves always show up first. Then you still see some energy coming through there, and then boom, the S waves hit, and then boom, the surface waves hit over here. So that's what you're seeing here are just these kind of big boom, boom, boom like that. All righty. So, oops, sorry. My leg itches. I had to scratch my leg. Sorry. That's what you're taking a look at here. So there's our P wave, there's our S wave, and these are the recorded seismograph from the 1989 Loma Prieta quake, but over in Finland. So you can record earthquakes all around the world with these super sensitive instruments. And I even have one in my basement. I have this thing called a Raspberry Shake, and this is some of the earthquakes I always pick up here. It's pretty awesome. It just runs in my basement all day long, records all this, and goes to a website. And we can, I've recorded earthquakes from everywhere around the world, which is pretty fun and pretty cool to see. So in the olden days, they used to have the old drum recorders like this with the pen and paper, but now we have just those electronics that can measure the vibrations. Your cell phones do something similar. You have accelerometers in your cell phone that you could probably download like seismometer apps or something like that in here, and you can measure the up and down jig. Well, you can't even see my phone in the picture, but it measures the waves if you hit it and the vibrations and stuff like that, which is pretty cool. All right. So if we want to find the epicenter of an earthquake and we want to know where it was, how do we do it? Well, first you need a seismometer, then you need to record the wave. And once we record the wave, then we can start trying to figure out where the P and the S waves are. And so on this one, we're going to make it really simple and just say that this first one right here is the P wave. This is the S wave. And so we can say, okay, here comes, whoops, where'd it go? There we go. Here's our P wave. Here's our S wave. And then we just calculate the time in between. How much time did it take from when the P wave hit to when the S wave hit? You do the measuring. And in this case, it's like 50 seconds or somewhere in that neighborhood. And luckily for us, geologists and seismologists have come up with kind of what we call this S minus P travel time curve. And we basically know how fast waves travel through different rocks. And if we know it took 50 seconds, we should be able to use the distance equals rate times time to figure out how far away it was. And instead of using the equation, they've just made this little chart, this S&P chart. So if it's 50 seconds between P and S waves, you go until it intersects that S minus P curve and go down, and it tells us, oh, this one was 480 kilometers away. All right, so it's 480 kilometers away. So what does that mean? That means if this is a seismic station in California that picked up that earthquake in Eureka, like that's where this one picked up this seismic station, that means the earthquake could be anywhere here on this big circle here. All right. So how do we know then where exactly on the circle the earthquake was? Well, you need at least 3 other stations and 4 to figure out the depth here to figure out where this was, because you'll see the circles intersect each other. So if you figure out these exact same circles for at least 3 different stations for the same earthquake, you can triangulate it, or basically the circles will intersect in one spot, and that's the epicenter. If you have 4 of those stations, it'll go down depth and give you a 3-dimensional view of it too, and show you exactly where the hypocenter was deep down. And luckily for us in California, we have thousands of seismic stations, and that's a really good thing for us to have, because by doing this, what I just kind of showed you and explained, computers and supercomputers can calculate the P and the S wave arrival times at these seismic stations in just milliseconds. And if you have a dense network of these seismometers, they can calculate where the epicenter of an earthquake is within like 3 or 4 seconds. Pretty quick, right? It's not always right in terms of magnitude, but it gets the epicenter and gets an idea of what that magnitude is going to be. And what's cool about that is then if we can calculate within a few seconds of where the earthquake epicenter is, and then send out signals like cell signals or things like that, computer signals, Wi-Fi signals at the speed of light, which are way faster than earthquake waves, we can send out to people and saying, hey, there's an earthquake nearby, drop cover and hold on. And that's how this early earthquake warning system is going to work a little bit later on. So I'm going to skip this part because we don't really need to see that. I just want to kind of end a little bit here with how the earthquake early warning system works and how we're going to stay safe. And so again, this is my friend Wendy. She's the one narrating this. And it's a fairly new video that just came out at the end of last year that describes our earthquake early warning system in Oregon, Washington, and California. So here's how it works.
What would you do if you have seconds to prepare for shaking from an earthquake that has already begun? More than 143 million people in the United States are exposed to potentially damaging shaking due to earthquakes. Most of our nation's earthquake risk is concentrated in highly populated areas on the active plate tectonic boundaries of the west coast of the continental United States. The U.S. Geological Survey operates the Shake Alert Earthquake Early Warning System, which is part of the Advanced National Seismic System. Shake Alert is not earthquake prediction, but a Shake Alert message issued by the USGS indicates that an earthquake has begun and shaking is imminent.
So this is the thing I want to mention again, just to double clarify. We cannot predict earthquakes. What this does is the second an earthquake happens, the stations start detecting it and can give advanced warning to people that are a little bit further away. And so what you're going to see here in this Alaska clip is this is a great clip from 2018 of these kids doing the exact right thing. They feel the P wave. The P wave came first and gave them a jolt. And then they drop cover and hold on. And after they do that, you can see the shaking go nuts. They don't have an earthquake early warning system up there, but if you receive a warning, this is what you should do. So that's the P wave, like, uh-oh.
With even a few seconds of warning, Shake Alert can save lives and reduce.
And then look how strong the shaking got after that.
Protective actions such as drop, cover, and hold on. Shake Alert further protects people and infrastructure by triggering automatic actions, such as slowing down trains to prevent derailments, opening firehouse doors so they don't jam shut, and closing valves to protect water systems, and to stabilize equipment during life-critical situations. How does Shake Alert work? When an earthquake occurs.
So this is part of the sketch notes, like, you know, hey, how does Sketch Alert or Sketch Alert, how does Shake Alert work in your sketch
Seismic
notes?
waves carry energy in all directions away from the epicenter. P waves, similar to sound waves, move quickly through the ground, followed by the slower and generally more damaging S waves and surface waves. Sensors detect the seismic waves and send that information to a Shake Alert processing center, which requires that at least 4 sensors detect the earthquake. If the earthquake fits the right profile, the USGS issues a Shake Alert message.
So that's a good point here, is not every single earthquake that happens needs a warning. If they're small and not going to be damaging, no need sending a warning for that. So most of the time, like in California now, I think the threshold is it has to be like a magnitude 4, magnitude 4.5 or so at least, and produce what we call shaking that's moderately strong, or expected shaking that's moderately strong. So if you're in any of those areas that would experience moderately strong shaking, you would get a warning. If you're too far away and you wouldn't expect to be shaken too bad, you're not going to get a warning.
Distribution partners then produce and deliver an alert to people and trigger automated systems. Alert delivery can be before, during, or after shaking from S waves and surface waves. Alerts can be delivered to people through apps designed for cell phones and other wireless devices, over public address systems, TVs and radios, and by FEMA's Wireless Emergency Alert System, WEA, which is also the source of Amber Alerts. For every earthquake, there is a region near the epicenter where alerts will not arrive before shaking begins. That's because close to the epicenter, the P and S waves are too close together, and the shake alert system needs time, often just seconds, to estimate the earthquake's magnitude and shaking levels before issuing a shake alert message.
Yeah, so if you're standing here, if you live right on the epicenter, even traveling at the speed of light after calculating everything, the earthquake waves will already be on you. So if you live really right here, right on it, it's not going to do you much good. But the farther away you are from it, it's going to give you more time to be safe.
That means that people close to the earthquake epicenter might not get an alert until after the shaking has already started. Those farther away from the epicenter could receive more warning time before shaking arrives. If an earthquake continues to grow in size, additional shake alert messages might be issued, updating the estimated magnitude and expected shaking for that event, which will result in alerts being delivered to a broader area. The USGS recommends that when you receive an alert, you should take protective action immediately. Do not wait for shaking to arrive. If you are near the coast in a tsunami-prone region, it's important to get to high ground quickly, but only after shaking stops.
It's
Before
too
traveling to a
it's
new
too hard to run when the ground is shaking. Let's just put it that way.
place, learn about both the local hazards and the recommended precautions to take by reading information found in the city, county, or state's emergency management websites. Knowledge of your surroundings and practicing protective actions are critical components of preparedness for any disaster. Always remember, if you receive an earthquake alert or experience shaking, drop, cover, and hold on until all shaking stops.
And next week, I'll show you, there's a poster too that shows everybody how to do it for all different modalities. So if you're in a wheelchair, cane, or things like that, like in a wheelchair, they lock the wheels and then cover your head with your hands and stuff like that. So there's other ways of doing that. And the reason I kind of show you that really fast, or this little slide, and I'll show you more next week when we talk about it. But just yesterday, there was on Twitter this video here that you can click on that shows a train in Japan. A bullet train was going like 100 miles an hour, got an earthquake early warning in Japan, and put the brakes on, and the train stopped and then started shaking, because you don't want these bullet trains going 200 miles an hour and to have an earthquake, knock it off the tracks and derail it going 200 miles an hour. That would be terrible. And we'll talk about Pakistan and damage here, but that was this week as well. We'll talk about that next week. So here's the one thing I just want to hammer home before we're done here, is that for this part, these understanding seismic waves will save lives. This is the official MyShake earthquake early warning app. If you download this to your phone, Android, iPhone, whatever, it will give you a big alert that says, are people getting kicked out still? That's weird. It'll give you a big alert that says, hey, earthquake, drop cover, hold on. And I've gotten 3 alerts so far, all of them for the earthquakes over in the Eastern Sierra, and nothing big shaking. But the first response is you hear it and you look at your significant other and you're like, what the heck's going on? And then oh, it's a warning, drop cover and hold on. And so then you look for a place to drop cover and hold on and wait for it, and not really understand how big it's going to be quite yet. And then, you wait, and then, okay, it wasn't that big for the first time. But now they also send out expected magnitudes and where they think it was happening to begin with. So if you download this, it'll help keep you safe, and you can keep your friends safe, your family safe, and all that stuff. And just I'll end with, these are my friends on Twitter that are all seismologists. You can follow them and learn everything you can possibly need to know about earthquakes from there. Ask them questions. They're super great, awesome science communicators. So these are the ones that you should talk to if you need it. So that's where we'll end for tonight. We talked about all these different things. You guys did so great hanging in there on a Friday night. I appreciate it. I see people are getting booted left and right and coming back. So thanks for hanging in there with that. We know what an earthquake is, the breaking and rocks, right? Shifting. Some of the notable historic quakes in California, just do a few of those. Tell me what they were. What's an epicenter? What's a focus or the hypocenter? Just give me a little schematic there. We did the 3 varieties of faults. We looked at body waves and surface waves. Showed you the seismograph of the P waves, then the S waves, then the surface waves. Then remember, you need at least 3 seismographs or seismographs and the locations of them, three of those to triangulate where the epicenter is. And then you can watch that little video clip again if you need to from the slides to show how that earthquake early warning system works. But it's basically, there's the fault ruptures, sends out the P waves and the S waves, and those seismic stations pick up the P waves and the S waves, calculates how far away it is, finds the epicenter, tries to figure out how much ground shaking there's going to be. They send it out to your cell phones if you're nearby, and tell you to drop cover and hold on to stay safe. So that's kind of how that would all go, but just try to find that, put that in a quick little sketch for a 6th grader here. So remember, we're not looking for Vincent van Gogh or anything like that, but just some good sketches that are kind of clean and neat, at least, that can portray those thoughts. So otherwise, we're going to end it here. You guys did awesome. You guys did great. Thanks for hanging in there on a Friday. Go Giants. I have no idea what the score is, but we'll see you this next Friday, I guess. So good job. Always email me or whatever if you need anything, and we'll go from there. So I hope you stay happy and healthy, and maybe we'll get some rain. Oh, and remember, it's going to be windy on Monday and Tuesday, so bring in all of your stuff. So that can blow away. Other than that, that's what I got for tonight. I'll see you guys later. Okay.
Good evening.
Bye, guys.